Hi, I'm Neil Tang, President of Antronics. We've collected a series of frequently asked questions that we get from technicians when we do training sessions for our new Milenium NXT 2 GHz taps and line passives. In this video, we will dive into the design, features of our product, along with some recommendations for conditioning and network architecture for optimal performance. We hope you'll find it useful. So let's start. Yes, the upper frequency band of DOCSIS 4.0 goes to 1.8 GHz, but our tap has an upper frequency bandwidth of 2 GHz. This extra 200 MHz of bandwidth ensures minimum roll-off in the upper frequency band. Also, the tap housing goes out to 3 GHz. This future-proofs your network when future technologies extends beyond the current 2 GHz we have here now. So you can simply upgrade with a simple faceplate swap. This is an extra insurance policy that the labor you use to upgrade your network now with a tap resplice will protect your investment for future technologies. The 2 GHz MHT series faceplate is not backwards compatible with existing tap housings in your network. The tap does need to be respliced for installation. The same applies for line passives. But these taps and line passes at 2 GHz are designed to match the insertion loss of your legacy taps up to 1.2 gigs. That's important because there is no system rebalancing necessarily when you need to do a passive upgrade from 1.2 GHz to 2 GHz. No, there are not. These taps have screwless Caesar mechanisms which have a higher frequency response. Caesar screws actually add capacitance to the interface and limits the upper frequency band of the tap. In legacy taps, you will need to remove the hex port plug, loosen the Caesar screw, install the KS pin connector, retighten the Caesar screw, and then replace the port plug. In the new 2 GHz tap, all you need to do is install the KS pin connector, screw it in to the proper 240 inch-pounds of torque. This reduces the number of steps from 5 in a legacy tap to only 1 step of installation in the new tap, thus improving your time of installation. Also note that the Caesar mechanism has 1,000 grams of retention force and has dual entry for both aerial and pedestal installation. No, the make-before-break bypass in the 2 GHz MHT tap provides uninterrupted RF and signal power when the faceplate is removed. These taps have a unique rocker mechanism in the bypass that guarantees no interruption of service even when the faceplate is removed or installed at an angle. This feature is critical in modern networks where installed smart devices such as RPD nodes are more susceptible to small power interruptions. This unique U-shaped rocker mechanism inside the bypass allows the faceplate to be removed and installed at an angle while this bypass can move up vertically. As you can see, as I'm pressing down on this, no matter what angle I'm pressing, that the bypass goes down up and down vertically. So if an installer is installing the tap and removing or installing the faceplate at an angle, as so, and pulling on the side bolt as opposed to the proper center bolt, that the faceplate can compress against this U-shaped rocker mechanism and enable the bypass to go up and down vertically to ensure a make-before-break for non-interruption of AC and RF power downstream. Yes, the white plastic dielectric does indeed stick out of the F connector in our tap. This is a unique auto-seizing cam port where the dielectric is compressed when the F connector is installed and the flanges grip against the center conductor of the coax cable, providing over 2,000 grams of pull force. Yes, if you cut the pin cut length too long or too short, this will affect your RF performance on the tap. It is critical on 1.8 gig taps and above that the pin cut length is correct. In old legacy taps, 1 gig or 1.2 gig taps, you can actually get away with eyeballing the pin cut length on the stinger. That RF performance is not as critical. But in these new taps, the amount of pin cut is critical. If it's cut too long, it adds inductance and capacitance to the actual connection and can actually degrade your performance. That's why we offer a cutting sleeve tool, the Antronix ACS-32, to help you assist in cutting the pin length. Here is the block diagram of a legacy tap. As you can see, this is a 2-port tap with AC going from input to output and the RF going through the directional coupler. This is the block diagram where you have a plug-in conditioner. As you can see, the conditioning socket is after the directional coupler. So this does not affect the insertion loss or through loss of the tap, no matter which conditioner you plug in. The conditioning only impacts the tap ports in the tap. As depicted, all tap ports are conditioned and cannot condition an individual tap port. Yes, they will help upstream and downstream. So there's different types of plug-in conditioners as shown here. The actual jumper is shipped with the tap as is, so every tap is actually shipped with a bypass. You do have a cable equalizer plug-in. These cable equalizers are used in lower tap values towards the end of the cascade. As you can see, there's more insertion loss in the low frequency band in a cable equalizer. This actually compensates for the downwards tilt that is at the end of the line. A cable simulator is installed in high tap values. This is close to the node or amplifier. Because node or amplifiers have a positive tilt, this is an equal and opposite slope with a downwards tilt to ensure that the response coming out of the tap is a flat response to the home. There's also conditioners that use a diplex. These are return step attenuators and forward path attenuators. But we do not recommend these diplex versions because these diplex versions will be problematic when you upgrade from subsplit to potentially a mid-split or a high-split upgrade. You would have to actually go back to the tap and swap out these conditioners, which is not recommended. So therefore, we only recommend the cable equalizer or the cable simulator if you're planning to optimize your upstream and downstream. So how do you use these cable simulators and cable equalizers? So a cable simulator is actually used in high tap values. In this example, you can see a 32 value tap. And this is a depiction of the frequency response before conditioning. So you have a positive upstream tilt coming out of your node. Because it's a 32 dB tap, the modem needs to overcome 32 dB of loss. Therefore, this modem is actually transmitting at a very high level, railing at the excessive high end of the transmit level. This modem level, in this instance, is a plus 49 dB MV. By simply plugging in one cable simulator into this tap, you can actually use a cable simulator 9 dB with a 23 dB tap and have a 40 dB MV upstream signal level. This actually reduces the upstream loss by 9 dB, where you still get a 32 dB in the forward band and a 23 dB on the upstream. This ensures your modem is operating at an optimal level. The cable equalizer plugin, on the other hand, is actually used in low value taps. As the signal goes down the cascade, there's typically a forward reverse tilt, a downward slope at the end of the line. What happens here is that the modem at the end of the line is actually transmitting at a low value because the tap is potentially an 8 dB tap or a 4 dB tap, a very low value. So therefore, the transmit level is, in this instance, a 30 dBmV at this tap level. So this low tap value causes a lower carry to noise and actually a potential for ingress on these low tap value locations. With a simple single plug-in of a 10 dB cable equalizer that has an equal and opposite tilt, the response coming out of that low value tap is a very flat positive tilt. Therefore, you have 10 dB more attenuation in the upstream band. Your cable modem will be transmitting 10 dB higher, in this case at plus 40 dBmV. Therefore, you have a 10 dB improvement of carry to noise. This plugin also blocks ingress by 10 dB at the same time. And as we all know, ingress typically occurs at the lowest tap values. So in your network scenario, you'll still have your 8 dB in the forward and an 18 dB upstream loss, therefore having a higher transmit level in the lower value taps. Here's a system node example before conditioning. As you can see, we have a cascade going from a 24 value tap all the way down to an 8 value tap. As you go down these cascades with a 100-foot P500 cable between each tap at these tilt levels of 18/10 at 860 megahertz over 55 megahertz, you can see that the upstream modem levels are 41 dBmV for the 24 value tap and all the way down to 30 dBmV at the 8 value tap. Because of the variations on the upstream levels, you could see that the modem upstream transmit level varies from 41 to 30, an 11 dB variation. By making two simple adjustments at the end of the line and plugging in two cable equalizers, a CE4 dB on the 15 tap and a CE10 on the 8 value tap, you're increasing the upstream modem transmit levels on those two homes to 40 dBmV right in the sweet spot. Therefore, your total upstream transmit levels only vary 4 dB from 41 to 37 dBmV. This optimizes your network for each customer across the whole cascade, has the optimal carry to noise for their home. With these tools available for conditioning, you have cable equalizers and cable simulators. You do not want to have these used in the field as a band-aid. So these tools should be used in the design stage with fixed amount of cable equalization or fixed amount of cable simulator into the tap. So please follow the design print and do not change them in the field to fix a small problem. To change in the plug-in conditioner in the tap, you would first remove the faceplate. Loosen up the 4 faceplate closure bolts. Remove the faceplate from the tap. Then squeeze the clips on the jumper that's pre-installed into the tap to remove the plug-in of the jumper. Select which plug-in conditioning filter you need to use, either cable equalizer, cable simulator to the correct dB value, and insert that back into the socket. Replace the faceplate back into the housing, ensuring that the faceplate is oriented correctly because it is keyed. Then you would install the torque to the proper torque sequence on the 4 closure bolts. The filters are packaged in tubes with a label. So you should remove the label from the tube and affix the proper label onto the faceplate so you know which plug-in conditioner is actually installed in the tap. The plug-in cable simulator CSH does go out to 1.8 gigahertz. Note that the plugins for the 2 gigahertz taps is a CSH, and it's a different plugin for the legacy 1.2 gig taps. The CSH has a cable simulator value at 1.8 gigahertz. So what dB value is listed in the model number is the actual cable simulator loss at 1.8 gigahertz. The plug-in cable equalizer is the CEH series. The CEH cable equalizer has minimum insertion loss at 1.8 gigahertz. This is the knee of the cable equalizer. So you do not want to use these if your network is in a 1.2 gigahertz balanced system. you're using a 1.2 gigahertz amplifier, you will have excessive insertion loss at 1.2 gigs. This is intended for use when your network has been upgraded with amplifiers to 1.8 gigs. In instances where you want to swap out your taps from 1.2 or 1 gig to 1.8 and your amplifiers aren't available yet, you use a 1.2 gigahertz knee version of a cable equalizer. This is the CEJ model number. So this actually is installed in our 2 gigahertz tap, but the knee is at 1.2 gigs. As you can see, the bandwidth does extend all the way through to 1.8. We've consolidated photos, datasheets, installation guides, and how-to videos for the taps and line passives all in one resource page for your convenience. Please reach out to your Intronics representative if you have any questions or need clarity on anything we covered here today. Thank you very much.